ZKVM.
Another one, man. They multiplying like spam.
Okay, we're gonna get started in 2 minutes. We have 74 people, 75 people on the call. Welcome Giacomo, Alp, Alim, Ziyi, Alessandro, Ango, Antoine. Lots of new names. That's fantastic. Welcome everyone.
Got curves, but the gas too thick. Mainnet choke, make your verify sick. Copy paste repo, another lame sequel. Tweeting benchmarks, bro, they're deceitful. You recursive, dog, please pause. Nested so deep, made Santa Claus lost. Back end sweating, chain haul drama. Verify slower than your grandmama. Prover killer, slaying every fake VM. Say you're modular, stacks looking shaky, man. Tweet proofs, but you can't even verify. Proof lab laughs while another ZKVM die. Every VC got a VM, they all the same. Control V, code base, Control C fame. You change a little field, wow, real clever. Still can't verify, yeah, me neither. Threads on blast, mainnet slow. Back end melt like Bay Bridge snow. Docs say trustless, that's so fake.
Say Alexa, play Prism.
Prover trying to load sounds like dial up. Chain froze up, devs in denial, bruh. Curve so niche, can't even scale it. Stress test heavy till your witness bailing. Spin figure eights, run constraints and break them. Boot up, stall, yo, mainnet faking. Docs on docs, blogs on blogs.
Okay, welcome everyone. We're gonna get started in about 15 seconds.
Say your modular stacks looking shaky, man. Tweeted proofs, but you can't even verify. Proof lab blast while another ZKVM. I drop entropy like E40 slang. Your prover crash, that's bang, bang, bang. Claim you're plonk, but you're just confused. Circuit sloppy, benchmarks bruised. Back end looking janky like scraper paint. Mainnet run, nah, it faint. Verifier gone, ghost in the shell. Another ZKVM bid farewell. Prover crying, CPU frying. Tweeting copium, whole team's lying. Docs still say, alpha release. Proof lab swing, VM deceased. Hey, Proof lab, ZKVM graveyard shift.
Okay, welcome everyone. We have over 100 people on the call. We're expecting more folks to come in. So this is Ethproofs call number 6. If you're new to Ethproofs, it's an initiative to try and accelerate the advent of proofs, snarks on Ethereum L1. Today's call is dedicated to proximity gaps, which goes to the foundations, the mathematical foundations of modern hash-based snarks. And we have a Telegram group, Ethproofs_community, with a QR code if you'd like to join this group. And that's a way to register for future calls. So so far we've had six calls on all sorts of great topics. And just to give you a sense for what's coming next, we're going to have a call on guest programs, formal verification, and alternatives to RISC-V. So today we're going to be discussing proximity gaps, specifically these 3 papers. They came over the last few days. It's been a great treat to have so many strong papers coming out, all one next to the other. And we're also going to be discussing the proximity prize, and I believe both Dan and Giacomo are on this call today. And above and beyond the papers that we're going to be discussing, there's just a flurry of papers related to proximity gaps that have landed in the last few days. So over the course of 6 days, I believe, we've had 6 papers. So that's 1 paper per day, which is pretty amazing. And I'm hoping that maybe we can organize Ethproofs call 6B, where we can discuss some of these other papers on the topic. I just want to give a few quick updates, and then we can move on to the content. So one update is that we've had a workshop last month in Cambridge dedicated to post-quantum cryptography. It's been a massive success. There's a lot of content that you can find on the internet, something like 25 hours of content on post-quantum cryptography, and the efforts, the engineering efforts that we're investing to get this stuff on mainnet. And it was such a success that we are going to organize it again next year. So we've already pre-booked the venue. Another quick update is that this ZKVM tracker is getting greener and greener every single week. So the top ZKVMs are those that have either integrated with Ethproofs or are expected to integrate with Ethproofs later this year. And the things that are highlighted in yellow are new developments. So Airbender is being proved by Matter Labs and Fermah. OpenVM has also been integrated to Ethproofs with Axiom as the prover. We have Silkworm, which is using SP1 Turbo. SP1 Turbo GPU acceleration is now source available if you want to have a look at what they're doing. And we also have SP1 Hypercube verifier that is now dual licensed Apache MIT. We have a new ZKVM that I just learned about yesterday called Toka Mac. And we have a couple ZKVMs that are still in development by a couple projects that disclosed this recently. And we also have two redacted ZKVMs in stealth, both of which are building lattice-based ZKVM. So super exciting development here with a new flavor of ZKVMs. Okay, and the second update I wanted to share is that in a couple of weeks on November 22nd, if you happen to be in Argentina for DevConnect, we have Ethproofs Day, so you can find more information on ethproofs.day or luma/ethproofs_day. We have a very exciting demo that we'll be doing on Ethproofs Day. Specifically, we'll be running a validator node verifying ZKVM proofs, and we'll be turning off the execution layer client and running only on a consensus layer client. And we'll have multiple provers proving every single mainnet L1 block in real time using a very modest number of GPUs in the grand scheme of things. And another piece of great news is that Farah has joined the Ethereum Foundation, and she is now leading a new team within the Ethereum Foundation called the Ethproofs team. So congrats and welcome to Farah. So this is today's agenda. We're going to have a few ecosystem updates before the hardcore presentations. And then we'll have 1.5 hours of presentation. So in total, we'll try and wrap everything up within 2 minutes. So we have a lot of content. Without further ado, I'd like to invite Justin Thaler to talk about Jolt streaming. Are you here, Justin? If not, we will move to Alan from Prism. Sorry, Pico Prism.
Hi. Can you see my screen?
Yes. Welcome.
All right, cool. Yeah. So I'll start. So hi everyone, this is Alan from Brevis. I'm pretty honored to share with you the journey to Ethereum real-time proving. Here a little bit of our journey here. So back in the day of at the beginning of this year, we just released our first generation of Pico, which is a moderate and performance ZKVM. And after that, we have been like moving all these kind of CPU computations onto GPU. So there's a bunch of things that we have been doing right here. So moving the heavy lifting parts. Since we have been building on the Plunky 3, there's like PCS commit, open, quotient computation, etc. All these computations are pretty heavy, and we move them all to the GPU so that for each of the phase we have GPU proving, while still the emulation and the trace generation is on CPU. But at this time, the single GPU is already pretty performant, and has no idle time. And then next step would be to move that to the multi-GPU version. So this is our second generation. It's the first GPU boosted version, and we link it to the Ethproofs at that time. And then going from single GPU to multi GPUs, what we did is to just try to find a better coordination between multiple GPUs and CPUs. And later we have figured out that trace generation is actually one of the bottlenecks there. So we moved all of them to the GPU to further boosting the efficiency. And then at the end of the day, the workload is almost achieved at a perfect balance. By perfect balance, I mean this is a machine of like 8 GPUs with 124 CPUs, and then either adding more CPUs or adding more GPUs will not further boost the whole performance. So that's what we call the achieving the perfect balance here. So they do have a pretty good balance of the workloads between CPU and GPU, and they communicate pretty nicely so that we were able to achieve pretty good results there. So, so there comes the Pico Prism, which is our third generation, which is essentially unleashing the power of computing clusters. So currently we are still working on the single machine, but now since we are aiming for real-time proving with accessible consumer-grade hardware, we went with the sub-block solution, which is essentially dividing one Ethereum block into several sub-blocks and proving them by divide and conquer. And then at that time, like we have 8 machines in total. Each of them have like 8 GPUs. And we let 7 of them to prove 7 sub-blocks and 1 of them to do the aggregation so that we have a pretty good divide and conquer scenario. And then all things, most of the heavy lifting part is already moved to GPU, so it's still a pretty good balance. So that's the results that we are showing here. Proving the Ethereum blocks on September 1st. In total, there will be 7,200 blocks there. And then on average, it is 6.9 seconds on average to prove all the blocks. And then a 99% 6 Ethereum blocks are proved under 12 seconds, and about 97% of them under 10 seconds. So it's the standard of the real-time proving. So several observations on what's next. Real quick. So doing this kind of sub-block thing are embarrassingly parallelizable. So that is to say the Pico Prism will be able to prove arbitrarily large blocks with minor overhead. So performance will stay almost unchanged. So we will still expect the real-time proving as long as we have enough machine for doing the proving for larger blocks. And then the emulation becomes the new bottleneck. So we are already on the way to do the optimization. And we believe that currently where we are is that we use a single machine, which is the 5090 machine, to produce Ethereum block proofs with average time of 14 to 50 seconds, which is already pretty close to the real-time proving. And then we expect that after the optimization of the emulation, like maybe like in 2 to 3 months, we will be able to achieve the real-time proving with 16 5090 clusters. That is, like almost all the blocks will be proven under 10 seconds. So that's the performance for foreseeable future in the foreseeable future. And then finally, we are constructing our Pro network. So please stay tuned. That's all. Thank you.
Amazing. Thank you, Alan. I don't see any questions in the chat or any raised hands. So I'll just ask one very quick question. What is your current emulation speed, and what are you trying to target?
So the current emulation speed is about 10 million cycles, and then we expect to do at least a 5-fold increase, so that will be like 50 at least. So yeah, so that's our target. Yeah.
Per second, so 50 megahertz. Is that right?
Yeah.
Okay, got it. Cool. Yeah, I know that some teams have gone much higher results, so it makes sense that this is the bottleneck. But otherwise, these numbers are amazing. Next up, we have Michael from Airbender. If not, we'll move on to Reza from Wholesum.
Hello, can you hear me?
Yes. Hi, Reza.
Let me share my screen. Hi. Okay. So the idea is to prove Ethereum blocks in a P2P setting. A single client node is responsible for fetching block data and preparing the stage for proving. There is also a set of prover nodes whose task is to generate proofs. We use libp2p for network formation and node communication. RISC subblock and its block division logic is used as the ZK EVM. Currently, we average at 1 megahertz on a single RTX 4090, which is obviously not really enough for real-time proving. Here, proving follows a two-step sequential process. First, we have to prove n subblock guests and then push the generated proofs into the aggregation guest and obtain the final block proof. We plan to only serve the Ethereum network, and this means that while waiting for the aggregation guest to finish up, n-1 prover nodes are idle. To counter this inefficiency, we are working on a plan that starts proving subblock guests for another ZK VM. With this, we believe that we can effectively obtain 1.5 proofs per block. Okay, this is it. Thank you for your attention, ladies and gentlemen.
Amazing. Thank you, Reza. And great to hear that we have such a project, I guess, from Iran, I believe. So covering many places in the world. And we have a question in the chat from Ores asking, how can we have embarrassingly parallel proving? And the answer has to do with sub-blocks, which is this idea of taking a big block, you chunk it into smaller blocks at transaction boundaries. And in Fusaka, which is the next hard fork coming in December 3rd, we're going to have a 16 million gas limit per transaction. Okay, Reza, if you'd like to stop sharing your screen, we can move to Vanishree, who will share updates about Fermah.
I think I need the request approved to, okay, I think now I can do it. Cool. Hey everybody, my name is Vanishree, founder of Fermah. I wanted to give a quick update on Fermah generating airbender proofs for Ethproofs, and our goal here is threefold. One is in line with what the goal of Ethproofs itself is, which is bringing diversity of proof systems to Ethproofs. And the second one is to showcase a specific strength of Fermah, and in this case, fast integration of any proof system. And to contribute to ZK Sync, which is Fermah's one of key projects that we have partnered with. With respect to bringing diversity of proof systems and to showcase our ability to integrate any proof system quickly, we started with RISC, which is a fairly complex proof system in the sense that it has its own prover network with its own storage layer, for example. There is a whole stack, and we quickly integrated RISC without using their stack at all. This is how we started integrating with, this is how we started generating proofs for Ethproofs. And secondly, we just recently, as I said, started generating airbender proofs. And this is a generous quote from our friends at ZK Sync. They, basically our ability is to, our tooling helps us integrate any given proof system with any complex workflow of different kinds of workflow steps very easily. And thirdly, our goal, of course, was, so this I want to also highlight the amazing work done by ZK Sync. Airbender has phenomenal proving times. And along the way of because of our continued partnership with ZK Sync, our goal also was to help them reach their goal, and we contributed in the best way we can, and we pretty much behaved as one of their team members and contributed things like fixes that were that went upstream, etc. This is my update. Thank you so much.
Okay, thank you so much, Vanishree. Again, feel free to ask questions in the chat, raise your hand, or even just unmute and ask your question. If not, we're going to move, in the interest of time, Jeremy, about running Linux on a ZK VM. Nice. Literally running Linux.
I think you might want to unmute.
Thank you.
We can't hear you. Go.
Apologies about that. Yeah. So anyway, what I wanted to show is basically we have a demo here of running Linux on the ZKVM. So what you're seeing here is actually a real Linux kernel booting. Basically what we've done is we've modified the ZKVM, adding the support for RISC-V S mode, which effectively allows there to be a separation between a user mode and a supervisor mode and a full MMU that contains virtualized memory. So by extending the sort of proportion of RISC-V that we are able to prove, we actually are able to boot Linux and actually log in here. What this does is it opens up, it opens up the possibility of running multiple processes. As you can see here, it provides basically full support for a very large number of different types of software. Like I think in terms of producing proofs for Ethproofs, I think state transition functions don't need an entire operating system usually, although this will open up the ability to run more managed languages very easily. But what we're moving toward is, for a lot of other use cases, this idea that the ZKVM isn't just executing a single executable, but actually this idea that the ZKVM can be thought of as like similar to a normal VM, where you actually like a Docker container, right? You actually give the ZKVM an entire container to operate on. We're also like working on, for example, a block device that's a Merkleized block device, and so on. And just as a heads up, right now what you're seeing is we have fully completed all of the witness generation. The prover is largely complete. There's a couple of additional constraints to get done, so this isn't like fully complete yet. But it's we're making excellent progress, and it will be we will have this in our next version of the circuit that we release. We will have full support for S mode, and we will have full support for a working Linux system. So I think that's pretty much it. It's mostly just a cool tech demo, largely. But we're very excited about this. And in terms of performance, what you're seeing, we should be able to prove live at the speeds that this current emulation is going at. We are making additional improvements to our execution layer to go faster. The adding of things like the virtual memory did slow down execution, but this is actually like effectively how fast it'll prove live. Also, the delay on the typing is a little bit induced by currently it's using polling for accessing the key inputs. But what's interesting initially is that also this entire system is fully deterministic. So when you run, it allows you to run Linux things in a completely deterministic way. The only non-determinism is the user input in this case, and that could also be controlled by sending in scripted things or so on. Anyway, that's it.
Wow, Jeremy, mind-blowing. Congratulations. This is super cool. We have one question. Can it run Doom?
Doubtless it can. In fact, what's interesting is that because the entire operating system is there, effectively not everything more or less works. As long as the operating system supports it. Now, of course, getting the frame buffer output might be slightly annoying. But yeah.
Wow,
Yeah,
super
hello,
cool. Go ahead.
okay. Right, I was just going to ask Jeremy. This is amazing. But what Linux distribution is this working on? Because I know like for RISC-V, there's only a few distributions.
So interestingly, for RV32, there are somewhat limited distributions, and this is actually like it's like a BusyBox version of things. Now
Right.
for when we go to RV64G, there's actually a full Debian distribution for RV64G that basically is almost as complete as the ARM distribution if you look at supported software packages. And so once we have 64-bit as well as S mode, you should be able to run a complete, full, totally modern Linux distro, all the compiler tool chains, the whole 9 yards. We've already run GCC inside this thing,
Right.
and everything, and it works.
Amazing.
Jeremy, thank you so much for this fantastic demo. Next up, we have Leo, who will share some real-time proving updates.
How do I stop share? Sorry, I'm just. My thing is not.
No worries. I think Leo has started sharing.
I can I see my screen? Can I
Not
see the
yet.
slides? Not yet. Okay.
Okay, try
Let me
again.
see. Okay, I'll try again. How about now?
Nope, still no. Okay, let's move to Emile, and then we'll come back to you, Leo.
Okay.
Okay. Can you see my screen?
Yes.
Okay, thank you. I'm going to share quick updates about leanVM performance. So leanVM quickly is a VM whose goal is to is an attempt to replace BLS, so at the consensus layer of Ethereum, to make it post-quantum. And so we need to be able to aggregate XMSS signatures and to have recursion. To do so, we need a lot of Poseidons. And recently, we passed the bar of 1 million Poseidon per second on a M4 Max using GKR. And we are still approximately at 15x overhead versus plain text Poseidon. In terms of XMSS, we are approaching the target of 1,000 XMSS proven per second on the Mac, and still at 300 XMSS per second on an old Linux laptop. And there is still this 12x overhead versus proving raw Poseidons without the VM overhead. In terms of recursion, there is not the full end-to-end system implemented. We only have one weir opening implemented. And that's mainly the bottleneck. We need a third of a second to prove one weir opening, which is still much slower than what we target to have the full end-to-end recursion for like a tenth of a second. So conclusion, the VM runs currently at approximately 1 to 2 megahertz on a laptop CPU, can probably do 2x or more in terms of purely software optimization. We are not too far away from 1,000 XMSS per second using purely software optimizations. For recursion, we will probably need more ideas. And recently, there is this nice write-up by Georg Wiese about making twist and shout work in the hash-based setting, thanks to lookup star-based approach, and potentially new precompiles like modular precompiles inspired by OpenVM or something like this. Thank you.
Thank you, Emile. I love seeing the charts just getting better and better every week at such a fast pace. And I find it mind-blowing that the overhead of proving correctness of Poseidon is only 16x. So that's the overhead of a full proof system. And Vitalik, several months ago asked, should we organize a competition to try and have like proof systems that only have an overhead of 10x, and I was like, you're crazy, Vitalik. This is not possible. But actually, he was his intuition was correct that we can do a lot with tiny overhead. Congrats, Emile, on all the progress. Next up, we have George, who will talk about the soundness calculator.
Hello, everyone. This is George from the EF cryptography team. And for the past 6 months, we've been looking a lot into soundness of ZK-VM projects. And, you know, there is many ZK-VM projects, and each of them is using its own weird soundness calculator. And it's quite hard to compare apples to apples like it's needed for this L1 ZK-VM project. So naturally, what we did is make another soundness calculator that is supposed to be universal. So it's on GitHub. It's under my profile, but we'll soon move it to the Ethereum organization. Through the help of various projects, we currently support RISC-0, MIDEM, Zisk. They are all Fry-based proof systems. You can go to the results page, and you know, for example, you can see for Zisk some of the parameters being used, and then you can see, you know, like the regimes and how many bits of security it has. So, you know, like you have the unique decoding regime, the Johnson bound regime, the broken capacity bound regime, and the if-stark heuristic, and you can see how many bits of security you get. And how we want to use this tool is sort of kind of make it use it to think how trickle upwards, like how we can get from this heuristic up to where provable security is for each project. So I just wanted to put this on your radar. We are going to be working on it this year. We still don't support the new results that we're going to be hearing about today. We don't support the 1.5 Johnson bound regime, which is kind of interesting. We don't support other PCSs other than Fry. So there is work to be done, and please get in touch if you find it interesting. But yeah, just wanted to put it on your radar. Thanks a lot.
Thanks, George. And yeah, this is a great initiative that should provide legibility for the whole industry, which is fantastic. Leo, shall we try again with your presentation?
Yeah, sure. Yeah, let's try again. How about now?
No.
Still no?
No.
Oh, that's
maybe
weird.
Maybe we can get Will to share the presentation. I think Justin Thaler might be in the chat. Justin, do you want to talk about Jolt streaming?
Yes, sounds good. Can you see my slides?
Yes.
Okay, great. So apologies for missing my slot before. So yeah, what is Jolt streaming? Let me, sorry, exit full screen here because this isn't, oh, there we go. Can you see the second slide?
Yeah, we can. Yeah.
Okay. So as probably everybody knows, the prevailing way of controlling prover memory today in ZKVMs is to break a big execution trace into chunks, prove each chunk kind of almost separately, and then recursively aggregate the proofs. You do have to kind of link the state of memory at the end of each chunk to the state of memory at the start of the next chunk. So that is a complication. So I want to start with motivation. Like why do I want to change how we do, this technique for controlling prover memory? The reasons are both simplicity and performance. I think there's a view that this way of doing things is fine. Everyone does it this way. I think that we can do better. On the simplicity side, this recursive approach, invoking recursive, proof systems everywhere is just a massive surface area for bugs. So let me just leave it at that. It'd be nice if we just didn't have that surface area. And then on the performance side, there actually is a performance hit to this. Some projects today are spending the majority of their prover time on the recursive proving, which means if you could get rid of the recursion, it actually, even if your non-recursive prover got 3x slower, it would still be a net win to not have the recursion. Other projects to link memory between chunks, they turn to elliptic curve based hash functions, and that gives up both speed and post-quantum security. So let me leave it at that. So we can hope to do better, right? Like everyone does things this way, but it doesn't mean it's the best way to do things. So that's the motivation for streaming. Today, Jolt is not streaming. That means the prover space grows linearly with the number of cycles being proved. Now it's still like, a pretty good space bound per cycle, 850 bytes or so per cycle at this moment in time. This means we need about a terabyte of space roughly to prove an Ethereum block, which is, just maybe acceptable for, the machines with the largest amounts of RAM. But we want to do better than this, right? The goal is to make the prover space, at most 2 gigabytes or something, regardless of cycle count. So where are we? So I hope to be a little further along and give you like a real update today. Unfortunately, we're not all that far along. So Jolt invokes the Suncheck protocol about 20 times. And if any single one of these 20 invocations need linear space, then, in total, we need linear space, right? So we have to go through each one of these 20 Sunchecks and kind of make it streaming. And so we've done 2 of the 20, and we've also made committing and evaluation proof streaming. So that's where we are. But getting the first 2 of the 20 out of the way is sort of the hardest part. So now to do the remaining 18, I think we'll be done in about a month. And then, hopefully we'll come back with awesome results. But that's all I have for today. Thank you.
Okay, exciting. Thank you so much, Justin. And I believe that is the main bottleneck to getting Jolt integrated with Ethproofs. So hopefully we can look forward to a Christmas present. Next up, let's try again with Leo. Perfect.
Okay,
You
yeah,
can see the slides.
I guess that we'll just share my slides, which is easier. So my name is Leo Fan. I'm from Cysic. So today I'm here to report some progress on or some updates on Venice. So Venice is a hybrid proof system combining GPUs and FPGAs, and we build based on the Hypercube proof system from Succinct. Yeah, so since last month, we integrate almost all these 50 plus chips for this trace chain, and we bring to GPU. So as you can see the table, compare with Hypercube performance, we somehow achieve around 500 times speed up. If you count this PCIe transformation, we still achieve about 30 plus speed up. And in addition to that, we also doing some fuse and unified most of the proving kernels into just a single CUDA C++ kernel, which bring another 15 to 30% proving speed. So the takeaway is right now, Venice is about 2 times faster, end-to-end compared with Hypercube, and we hopefully by estimation we can achieve real-time proving on using just 70 1480 GPU cards, and our goal is to push the limit to 32 1480 GPU cards. Yeah, so that's all. Thank you.
Thank you, Leo. And yeah, this is a super cool approach to have a dual FPGA and GPU. And yeah, the numbers that you showed me just a couple of weeks ago were really, really impressive. These speedups are pretty insane. So congrats. Is Michael on the call to talk about Airbender, or anyone from Matter Labs?
I don't see Michael here. To be honest, I'm not sure what he wanted to present here. Do you have a topic from him, so I may try to cover it early?
Yeah, the idea was just to give a flavor of the next generation of Airbender.
Well, I mean, so for the next generation, his message to me this early morning, so late evening for him, was that he finally finished the largest GPU piece of code which is needed for the next version. So the one which is on Ethproofs is the old one, back from April-ish, something like this. So it was done just for fun by Martin. So he did it all by himself to try it. We never actually planned to do it on the old version, but he did it all by himself. And so for the demo day, Justin, as I explained, we will try to get the new one in. It's tested like CPU on full Ethereum blocks, so it's fine, conversion all the way with the recursion. But we needed this piece of GPU code from Michael himself to finish, and we will try to fit into the next 2 weeks to get everything in. The slowest part is still a simulator, but for this one, we don't have capacity to improve right now, so we should have Maybe not the base latency in absolute numbers, but good throughput.
Okay, super exciting. So I guess what you call the old prover is still like the fastest on Ethproofs by a factor of 2x. So looking forward to the performance of the new version.
Yeah, Michael
cool.
was like, most likely was just working all the night to get this message today in our Slack. So most likely he's still sleeping.
I mean, just in general, I want to say thank you to all of the ZKVM teams that are really, really grinding extremely hard in this very competitive environment. And the performance is insane. And they're all working towards this big demo for DevConnect. So thank you so much to all the devs working so hard. Cool. We're done with the ecosystem updates. Now for the mathematics. So I'd like to invite Ziyi to talk about the first paper on distance preserving generators.
Thank you. Let me just try to share my screen. Okay, can you see it?
Yes.
No, this doesn't. Amazing. Here. Okay, great. So you can see the screen.
Yes, we can see it.
Okay, great. Okay, so hello everyone, I'm Ziyi. So I'm gonna give a very, very brief overview on our recent paper we submitted to ePrint earlier yesterday. It's gonna be online soonish, I think. And the topic is about polynomial generators, and in particular their distance preservation property, especially their mutual correlative agreement. This is joint work with Sarah, Ale, and Ignacio. So let me start with defining the problem. So what is distance preservation? It's usually defined with respect to a linear coach with minimum distance delta. And then usually we're given just a batch of vectors, UIs. And the goal is to check each one of them, whether they're close to the linear code or not. And however, in applications, it's usually like not very cost efficient to kind of check them one by one. It's going to cause a lot of randomness complexity, verify running time, so on and so forth. So then one kind of systematic method that people developed to do this type of checks, especially when the vectors are given in groups, is to check their linear combination instead. In particular, one abstraction for this kind of linear combination approach is to consider a generator, which is a function that takes a seed and maps it to L coefficient. And then we use this coefficient, the output of this function, to do the linear combination of all the words we want to check and arrive at this UX. And then we check how close UX, the combined word, is with the linear code. And in particular, what we want is that if the combined word UX is not super far from the code, then we know that all the words that we start with are also not super far from the code. And one way to formalize this is to use mutual correlative agreement. And intuitively, what does it mean? Again, we have a generator that takes a seed. And for simplicity, let's assume that the output is two coefficients, alpha1 and alpha2. And I have two vectors that I want to check to start with, the green one and the dark blue one. And I just use the generator output to compute the linear combination of these two words to arrive at this light blue one. And I check how far it is from the linear code. And now, as the picture shows, like at 4 positions kind of specified by the arrows, they agree with the code. The mutual correlative agreement enforces that if that's the case, if those 4 positions are the ones that the combined code word agrees with the code, then it has to be that these 4 positions are fine in the original code words, the original words that we start from. And this can be formalized by this property called mutual correlative agreement. And in this paper, one of the central questions that we study is we want to figure out what type of generators have mutual correlative agreement, either for general linear codes or for specific linear code. And in particular, it's considered the universe of all generators. And prior works have studied a lot of different generators, like the affine space one, the affine line one, univariate powers, even like all multilinear monomials. And just by inspecting the definition of MCA and also structures obtained by previous papers, it's not so hard to see that having a generator to be zero evading is necessary, which means that you take the generator, the probability that the generator maps a non-linear vector to a linear vector is very, very small. This is a necessary condition. But is this sufficient? The answer we give in this paper is that a subclass of it, what we call polynomial generators, meaning that the output of the generators are composed by linearly independent polynomials Pj here. All those polynomial generators have mutual correlative agreement for linear codes. And in particular, it covers all generators which people previously studied their distance preservation property before. But which means that polynomial generator is a sufficient condition. But we also realize that it's actually not necessary because we also additionally studied this generator, which is not a polynomial generator for the first time, but we still establish its mutual correlative agreement for arbitrary linear codes. And then we, of course, specialized our result for Reed-Solomon codes as well, and we obtained more fine-grained bunch. And in particular, what we show is that all polynomial generators, again, everything included in this picture, have MCA for Reed-Solomon code up to the Johnson bunch. And in particular, it matches the best bunch. The best bunch as of like 5:07 a.m. Swiss time this morning. For correlated agreement for this two specific generators for Reed-Solomon codes. And ePrint is going to come soon, and thank you so much.
Just on time. Thank you so much, Z. So we have a question. What is phi x to the power j?
Phi, this one?
Yeah, yes.
So this is kind of a slight abuse of notation. I didn't introduce it, but basically you can view it as somehow like the univariate powers generator, but we just need to do some field isomorphism to make the domain works. But if you're interested, I can share this offline, but I don't think it's too meaningful to get into the details right now.
Cool. Ben is asking, what range of proximity parameters are your results operative for in the case of general linear codes?
Pardon? Which... Okay, let me see if I can see the question, actually.
It's in the chat, but Ben, you're welcome to unmute as well.
Which range are your results? Okay, for the specific bound, I actually do have a slide for that. And in particular, for example, in the affine space case, this is the bound we get. And in particular, it does match with the previous best bound for mutual correlative agreement obtained for this generator. And in particular, for general code and general polynomial generators, this is the bound we get, which is, there's a reason I don't want to talk about this within 5 minutes. The bound is complicated. But in general, for all the generators that I have in this picture, every bound we achieved in this paper match the all the bounds in prior works, except for this new paper by showed up on Ethproofs this morning.
Perfect. Thank you so much, Z. So I guess we have two classes of papers. We have those that have positive results, those that have negative results. This is one of the positive results. And next we have, I guess, a negative result from Angus and Ben, and their paper kind of did the rounds on Twitter for the last few days, and I think is a great wake-up call, all while still giving us hope that we can still squeeze a lot of juice with the remaining conjectures. Angus, the floor is yours. If you'd like to share your screen.
Okay, great. Has that worked?
Yes. Wait, not yet. Yes, now we can see it.
Okay, great. I guess as a first thing before I get into it, like a massive thanks to Justin and Will for organizing, I guess, the conference in Cambridge, from which I think this work came out of it, and also all the work regarding the proximity prize. It's been sort of amazing how many papers have come out in the last week, and slightly terrifying. But so the idea of Ben and me was to basically, one of the hard things about studying proximity gaps is you have all these codes and there's like lines between codes and you've got these polynomial relations, and this is really hard. So we thought, what if we just take a step back and only think about randomness? Just pick random words and ask, how likely is it for a random word to be close to the code? And the sort of surprising result that we show is that actually the answer is it's a bit closer than you expect. So, okay, so to give a brief picture, and I think this picture is still valid, but it may have been upended in the last week. So I apologize if this is slightly wrong. But roughly speaking, what do we know about proximity gaps? There's sort of three regimes that we knew a lot about. The first is in UDR, which is the green, and in LDR, which is the blue, where we have these nice proximity gap results that have just gotten a bit nicer as of this morning. And the other thing we knew about was in capacity. So this is this black regime. And here proximity gaps is just impossible because, I mean, it's vacuous. Every single word you pick is close to a code word. There's sort of no meaning to the statement. And essentially what the proximity gaps conjecture was if you look at the sort of the white area in the middle, how much of this white area can we push out? How far close to the black area can we get with these proximity gaps results? And what my and Ben result shows is that while we might be able to push it out somewhat, there is a small sliver away from this black region where proximity gaps simply aren't going to happen. And they're not going to happen basically because what we find is that in this red region, which is the size is roughly proportional to the one on the log base of your prime, in this red region, just random words are way too close to the code. And so proximity gaps breaks for these sort of very simple or random reasons. So I think probably the key thing to understand how our result works is the following theorem that we prove, which says if we have some statement about the probability that a random word is close to the code, this gives us a lower bound on the proximity gap error. And so I think a great question is like, why is this true? And this is true from sort of a pretty simple counting argument. The idea is you take some word which is far from the code, and now you partition your space into the set of all lines passing through this word. And so basically a simple thing about partitions is that because this is a partition, the proportion of sort of close points on one of these lines, at least one of these lines, this proportion has to match or be bigger than the proportion in the entire space. And the proportion in the entire space is exactly captured by this probability function. And so what this says is that there needs to be a line with a large proportion of close points on it, which is exactly a line that sort of breaks your proximity gap. Now, a very open question here. So currently we've managed to restate sort of trying to bound this error function in terms of trying to bound this other probability thing. And so there's a question, well, is this easier? How easy is it to sort of estimate what this probability that a random word is close to the code is? And for that, let's first turn to the sort of simplest case. So if we take our codes to have k equals 1, so this is where all of our, it's Reed-Solomon code, but actually all the code words are constants. So everything is just the repetition code. And additionally, we're going to take h equals 1. So here, h is the shortfall. So what does this mean? So if you take any code, right, there's always going to be a character appears once. So the maximum distance away from the code is going to be n minus 1, or more generally n minus k. And h is trying to capture how much extra is it going to extra close outside of that initial bound are we? So sort of how far kind of closer than the maximum distance are we? And so in this case, when you take h and k to be 1, then this probability becomes what is the chance that a random word U of distance n minus 2? And this is exactly the same to saying what is the probability that the two entries of the random word are equal? And if you sort of think about this for a second, this is the birthday paradox. you take sort of, 30 people in a room, and your word here is simply the vector of their birthdays. And you say, well, what's the probability that 2 birthdays are equal? And so in this case, there are sort of 2 things to know. Firstly, we can actually compute this probability exactly. But also, one of the takeaways from the birthday paradox is that actually sort of the number's higher than you expect, right? You need about 23 people in the room in order to get a 50% chance of 2 birthdays being equal. So this sort of gives you an indication that actually it maybe isn't so surprising that in these codes, you end up a little bit closer to the code than you might naively expect. So obviously this is a very simple example, and I'm mostly going to be talking about sort of heuristic picture here. I'm not going to go into so much the hard maths. That's going to be Ben in the second half of the talk. So one question is, well, how do we use this to make some estimates in the more general case? And for that, I'm going to use 2 assumptions. And roughly speaking, I think one of the results from the rest of our paper show that these assumptions are roughly reasonable. So we're going to let X denote this random variable, which is equal to the number of locations in which sort of our fixed code word and a random variable agree. And so we're going to have 2 claims now. The first is that if we take 2 different code words, V and V prime, these random variables behave like independent random variables. So one thing that I think mathematicians many people will immediately see is that this is clearly false in general, right? Some of these code words are sort of, they can be equal at points. But it turns out this isn't a bad approximation. And the second claim is that these independent random variables look roughly like they're Poisson distributed. And this one's more reasonable. This is sort of a general, like large Poisson approximation to the binomial distribution. But the key point from this is that what it allows us to do is it allows us to write the left-hand side, the probability that we're close to the code, in terms of this fancy P, where this is just the probability that we're close to a particular code word. And the statement is that the probability you're close to a particular code word is much easier to compute. So the first question is, well, is this approximation any good? And so what you can see here is, for the birthday paradox, we can compute all these things exactly. And you can see, so here what I've plotted on the x-axis, this is sort of the n, so the number of people, and the y-axis is the probability of having 2 people with the same birthday. And you can see that these all line up very well. So this is like a pretty good approximation in this case. And so hopefully you can sort of believe that this is a good approximation more generally. Now, what we can then look at is, well, what happens when we sort of fiddle around with our k and h values? And so here I've chosen a much bigger p. So in the birthday paradox case, p is 365. Here I'm choosing it to be about 60,000. In our proof systems, it's like 2 to the 128, but the same pictures will sort of apply. And over here, what I'm graphing is basically each of these lines corresponds to like a different value of h. So the red line here says, what's the probability we're sort of 1 closer than we expect? The blue line is 2 closer than we have to be. The green line is 3 closer. And what we can see is that sort of when k equals 1, we need to get n to be about 1,000 before we end up to be sort of 1 closer than expected. But all of a sudden, when k sort of rises to 2, the distance away we need to be goes from 1,000 to much less. It goes to about 100. And we can play this game as we keep increasing k, because in practice, k here is telling us the size of our code, and we usually work with quite large codes. And so you can see that as you keep increasing, sort of here I've slightly changed the picturing scheme. So because as we get to larger values, we're going to find that we're not only like 1 or 2 closer than we expect, we're like 50 or 100 closer. But you can see that as k increases, basically the value of n you need to pick such that you all of a sudden start becoming much closer than you expect rises quite quickly. As you can sort of keep going through, and you see once you pick k to be, say, 200, you find that if you have n to be around 1,000, you're about 80 closer than you expect. So you actually do get a fair way in from this capacity bound. The other thing you might note if you sort of look at these is that these lines are getting very steep. They start off sort of slanted, but eventually these basically become these sort of thresholding values. And so one of the questions we want to answer was, well, can we estimate where these thresholds are? Because these thresholds are basically where we think proximity gaps is completely doomed. And so basically through our work, we get this rough estimate of the thresholding value, where here eta and rho are relativized. So here eta is h divided by n, and rho is k divided by n. But this gives you a reasonable estimate. If you plug in a rho, this says, well, if you have less than sort of eta shortfall, you're almost guaranteed to be close to the code and proximity gaps is doomed. If you have more than eta shortfall, then our attack won't really work, which is, I guess, is good news in some ways. And so you can then take this and ask, well, how does this change actual in production snarks? And we get this sort of simple table. And basically what this table is saying is that if you want to use the conjecture of proximity gaps up to capacity, you should sort of adjust this a little bit by our results, and you should increase the number of queries by, in the row a half case, by 3, in the row a quarter case by sort of 1. And you can play around with this with sort of different numbers to work out exactly where. So this isn't a big hit, but it also is a hit. And I think it's also worth thinking about this and trying to work out, does it make sense to exist all the way over here? Or should you maybe be a bit closer to Lister coding? And I think this is one recommendation we'd have is, if you can, we'd definitely recommend trying to operate in proven securities regimes, particularly now that the proofs are getting so much stronger. Okay, I'm going to pause for now and switch over to Ben, who's going to cover some of the math side of things. How do I?
Okay, so I just tried to share. Is that going through?
Yep.
Okay, so thanks, Angus. And I want to reiterate the gratitude we both have for this workshop and also the Proximity Prize. I think has been amazing to see all these works that have been coming out. So really cool stuff. So let's get into it. So as Angus said, we have an overriding problem we want to talk about, which is that the probability that a random word will be close to the code, and in particular, closer than it kind of has to be. Okay, so the capacity you can think of as the covering radius. It's sort of the farthest that a word can be. So a word will not be farther than that, but will it be as far as it can be or closer? And essentially what we want to show is it'll be much closer than it has to be, than the farthest it could be. So here's a probability we care about. Symbolically, U is the random word and Z is a radius. And as Angus said already, if this probability is high, then the proximity gap error also is. So it's enough to just talk about this. Visually, just very crudely, right? So FQ to the N is a kind of box, let's say, and within it, we have these points, which are code words. Around each one, we inflate a ball of radius Z. And we're going to take a random word. And the question is U the random word in any of these balls or not? So this U is far from the code. And this one, say, is close to the code. The question is, if we pick U randomly, which of these two cases is liable to happen? So as you could see from the last picture, this probability we care about up to dividing by Q to the N is just a union. We care about the mass, the probability mass of this union of balls. So by the standard inclusion-exclusion principle, we want to bound the union from below. To do that, it's enough to look at the first two terms in this inclusion-exclusion sum. The first is just a raw sum of all the ball volumes, excluding overlaps. And the next is a kind of pairwise intersection term. If we look at these two terms, this gives us a lower bound on the union. Okay, so as a kind of cartoon picture here, if we care about this gray union on the left, we can add up the individual balls and then subtract off these pairwise intersection terms. Okay, so to do this, we're going to tackle these one at a time. Okay, so we want to lower bound the sum term and upper bound the intersection term. That's essentially the program of what we're going to do. So first things first, bounding the sum from below. The sum is actually pretty simple. We just take the number of code words. If we can learn the volume of one ball, we just multiply that by how many code words there are. So we turn to the ball volume. This is an extremely classical subject. This is kind of the standard approximation for the ball volume. It's two-sided. You could, for example, Mac Williams and Sloan, classic 1974 textbook. Now, actually, this is really not good enough for us for the following reason, right? So this is a lower and an upper bound. If you divide these, so the multiplicative gap between the upper and lower bounds actually looks like this root 8n term. It actually goes to infinity as n grows. So these are drifting apart from each other. We actually need really sharp control. We need an asymptotic estimate. So in short, we have this theorem. This expression looks a bit nasty. Actually, it turns out to be quite usable, arguably more so than this one because it has no entropy function. But more importantly, it's asymptotic, right? So the ratio between the ground truth here on the left and this expression actually goes to 1 if Z, Q, and N are chosen in such a way that these expressions become small. We call these controller expressions. If you choose Z, Q, and N so that these go to 0, then this ratio goes to 1. So that's really important for us. And even concretely, you can see this thing in action. So it's actually not hard to find parameters where this thing is already outperforming the classical entropy estimate. Here's Q equal 365, continuing the kind of birthday analogy, and N also 365. And you can see that when Z is closer to N, for these high radii Z, we're already outperforming the entropy lower bound in the sense that we're closer to the ground truth than the lower bound is. Still below the ground truth, but close. Okay, so turning to intersections. We want to bound this from above, and to do this, we do a couple combinatorial things. So it's pretty straightforward that if we're interested in all pairs, V and V prime, there's a kind of translational symmetry. We can actually just look at the 0 ball and then non-zero code words V and ask how those intersect, and then multiply by Q to the K. And moreover, the intersection between 0 and V actually only depends on the weight of V, how many non-zero components V has. So it's enough to partition this sum into weights and then study a few combinatorial things. So this is what we do. First, for each weight W, which must be at least D and going up to N, how many code words are there of weight exactly W? This is not too hard to do. Actually, this is the only place in the whole paper where we use the MDS assumption. It's kind of funny. Now, for each W, moreover, what is the size of the intersection between the ball around 0 and the ball around V, where V is of weight W? This is not crazy hard. It's a bit tricky. It's a bit combinatorially intensive, but we can do this as well. Really, the hardest part is to bound this weighted sum, and this requires a couple tricks. You'll see here again more of these controller expressions. So what we state is that this sum and our estimate for it, the ratio goes to 1 if these controllers become small. How do we do this? Combinatorics, of course. Here's a picture from the paper. Essentially, what matters is the weight of V, which we call W, and this other quantity S. Basically, S is a technical value. It says where U disagrees with 0, how many of those disagreements happen at a place where V also agrees with 0, something like that. What we show is that actually there's a double sum, and one of the summands ends up dominating the entire double sum, at least for Z close to N, or when the controllers get small. Okay, so that's a speed run of our lemmas. Here's our main theorem. What we're going to do is we're going to let N drive to infinity. We're going to specialize, and then as a function of N, we're going to tell you what Q should be, and also what Z, the radius, should be, and what K, the message length, should be. The claim is that as N goes to infinity, first of all, these specializations make our controller functions get small, so our estimates become sharp in the limit. And moreover, the intersection term divided by the sum term actually goes to 0. So this means we've thus rigorously shown that you can ignore intersections. That needs to be done precisely, but we do. So the last thing standing is just the first order approximation, the sum term. And what we show is that that thing actually decays slowly, actually more slowly than N to the C over Q, which is enough to prove the theorem. So here's a bit of a visual explanation. It looks a bit crazy. Here you can barely see it because it's covered by the orange, is the actual lower bound with intersections. The orange is the first order term that ignores intersections. Now these are essentially identical. You need to prove that you can ignore intersections, but we do. You can see that they make effectively no difference. Now we're going to lower bound orange in a sequence of steps. Eventually, we get to this guy, the green. Actually, we go first to purple, which eventually becomes bigger than black here at a kind of predictable crossover, around 10,000 for us, but it can all be changed. So, and then finally bigger than green. And this way down here is n to the c star over q, which is actually 1 over n. We just choose q to be n to the c star plus 1. So we're blowing this out of the water here, this purple. You can see that certifiably orange is decaying more slowly than purple is. So that disproves the conjecture. Okay, looking ahead, we did propose a revised conjecture. Basically, what we want is our rates, our relative rates, and what we call the shortfall. So the shortfall, again, like Angus said, is how much smaller than the covering radius is the ball radius. So we want both of those to stay away from 0 as n goes to infinity. Basically, here's our conjecture. And our constant c, this looks like the Benz-Hassan et al. Conjecture, but c and k depend on rho and eta. Now, I thought that this might fall as of this morning. I thought it might be a short-lived conjecture. Actually, my best understanding as of now is that this conjecture is still alive, even despite the great new work that came out. So that's it for me. So I guess we can turn to questions now.
Fantastic. Thank you so much, Ben and Angus. Feel free to raise your hand or unmute. I guess one question I have is, as far as I can understand, there's like 2 other papers that have these negative results. Are they basically the same idea, or are they different ideas that could be combined to have an even stronger negative result?
So I know at least the one other paper by, was it Elizabeth and what's his name?
Alistair.
Alistair, yeah. So I think that paper is actually answering the same question to ask of what's the probability that a random word is close to the code, but they use sort of quite different methods. But I mean, sort of nicely, we end up with sort of similar takeaways of you need to bound your distance away from 0. I think they might have slightly different constants, but I think morally they're roughly the same. I don't know what, do you mean the other paper is one that came out this morning?
Yeah.
I haven't, yeah.
I can try this. I think we've all had it at most, I don't know, a couple hours to process this paper. I think, well, I guess Swastik I see here is on the call, so maybe he can tell us. But I think there is a result there that does disprove the original capacity conjecture. Using, of course, I think the techniques are very different. I also think it's characteristic specific, whereas and maybe domain specific, whereas ours is not. Ours is more of a generic combinatorial argument. I believe, and I think so. I believe that our current conjecture is not disproven by the new results. But maybe I should let Swastik tell us the real truth here. Maybe, if he wants. I guess he's it. So that's all I'll say for now. I guess we don't fully know, but I think yeah, a lot of things going on.
Okay, I just want to give a few seconds for people to ask any other questions.
Oh, I do see a question. It says, are these conjectures just related to proof sizes, number of queries, or are there other impacts? So yeah, I think the main impact is proof size, mediated by number of queries.
Remco has a question. The conjectures are for general codes or general Reed-Solomon codes, but in practice, we are only interested in specific ones with cosets of roots of unity as evaluation domain. This weakens the conjecture. Could that change things?
So
I think,
yeah, go ahead.
Oh, okay, sure. I mean, yeah, I think so. So for our results, basically completely don't care about any sort of what you pick for the domain or honestly any of the parameters. It's sort of purely randomness, but there's like almost no algebra in it. That means that there was a big paper that came out, I guess, yesterday by Guruswamy about random Reed-Solomon codes. And so it does seem like the random case might be different to the specific case, but I don't think we currently know. Like, so I think the answer is plausibly, but we don't know enough.
Oh. Infinitude of primes. Okay, so this is a bit of an odd and interesting aspect of our proof technique. So what we're doing is we're specializing Q, K, and Z as n goes to infinity in certain ways. Actually, I can go back, or I'm not sharing anymore. So
Ben, would you mind repeating the question? I don't see it in the chat. Maybe it was a
paper,
private.
you mentioned the infinitude of primes inside a certain interval. Can you explain how this fact is relevant to the proof of your main result, and how does it relate to the conjectures we discussed? Okay, so how can I say this in simple terms? Basically, we let n drive to infinity. We define Q as a power of n. All the numbers shake out combinatorially, but there's a kind of odd technical problem, which is that Q might not be a prime power. So in order to disprove the conjecture, we need these to actually be Reed-Solomon codes that we're creating as n gets large. If Q is not a prime power, this doesn't really make sense. So it turns, so we could start rounding, let's say, let Q be the smallest prime power that's bigger than such and such. Our bounds are very delicate, so we don't want to push numbers around by rounding them or taking floors or ceilings. So instead, it turns out to be simpler to just say, well, maybe n is already prime. Maybe Q is already a prime power. And the question is, will that happen for infinitely many n along the family that we defined? It turns out that in order to guarantee that, you need there to be a prime in some certain interval. So the question is, as we go up to infinity, as we pick a bunch of intervals that are growing, but growing a bit slowly, the width is growing like x to the 2/3 or something. Can we guarantee that there will be primes in those intervals? And the answer is yes. This actually goes back to some kind of classical analytic number theory from the 1900s. So this is a bit of a technical obstacle that turns out to be not an obstacle. Could we bypass the number theory? Maybe. I think that turned out to just cause more problems than it solved. But I don't view that as essential to our proof. Kind of just an interesting side quest. If I'm not sure if that answers it, I'm happy to discuss more offline if anybody wants to talk.
Okay. There was one other question. What does it mean to partition the sum by weight of V? I think what we mean by that is just sort of so we're summing over all code words. And what we're saying is sort of two things. Firstly, so the weight of a code word is the number of non-zero elements. And our claim is that like the contribution to the sum depends only on the number of non-zero elements, not sort of the actual structure of the code word outside of that number. And so what we say is that like, instead of trying to like do these things for every code word, we just sort of pick a canonical representative with some number of non-zero elements and then count the number of code words with that number of, with sort of that structure. So sort of, it's a way of simplifying the work for us, I guess.
Right, and then right. So the non-zero elements are the parts of the partition, right?
Yeah,
okay.
Yeah.
Right, and just another question about the conjecture itself. The conjecture, to be honest, like combinatorially, seems to sort of like be believable, because even if you just think about the trivial bound on binomial trails, I think you do sort of come to that sort of KNC over Q. I can't, of course, calculate it immediately, but it seems to be combinatorial believable.
Yeah, so you mean our new conjecture?
Yeah, 5.1, yeah.
Yeah, I think, oh, sorry, you want to go back?
So are you're talking about how the binomial coefficient, I don't know, like NC behaves like, I don't think that's the right way to go here, right? Because for us, C isn't, that would make sense if C was like the distance or the proximity parameter or something, but that's actually not what's going on. Like for us, the proximity parameter is actually growing linearly in n. That binomial coefficient will not be bounded by a polynomial in n, right? That's actually going to probably be exponential. In other words, if I take n choose gamma n, where gamma is some fixed real constant, that will not be polynomial in n. So I see what you're saying, but I don't think, I think that might be not the interpretation you want.
Okay. Okay.
Ariel asked, your possibility result is for any MDS code, not just Reed-Solomon, and the answer is yes. Okay, thank you so much, Angus and Ben. Fantastic result and presentation. Next up, we have Swastik, who will be talking about his new paper that landed this morning. And various people regard Swastik as basically the world expert in proximity gaps. So Swastik, the floor is yours. We can't hear you. You might be muted.
Hello? Can you hear me now?
Hello. Yes.
Okay, great. Okay, so I'm going to talk about a paper from just this morning on proximity gaps for Reed-Solomon codes. This is a joint work with Emile Ben-Sasson, Dan Carmon, Ulrich Habak, and Shubhangi Saraf. And so we have a bunch of positive and negative results. And so I'll tell you a bit about some of them, and I'll tell you some of the, I'll tell you one of the ideas that goes into the proof of it. And you please ask me questions as we go. Okay, great. So the setup for proximity gaps, I just want you to get used to my letters. So C is a linear code. And I'll say C has proximity gaps up to radius gamma with proximity loss epsilon star with A exceptions. Okay, these are my letters, gamma, epsilon star, and A. If the following happens, whenever you have functions, oh, can I point? I'm trying to point. Oh, I can't. Oh, I can point. Yes. No, I can't. Okay, so I'll just, whenever you have two functions f and g, such that there are many combinations f plus zg which are close to the code, there are more than a of them, then f and g are jointly gamma prime plus epsilon star close to the code. Is that okay? So I have a gamma prime sitting there, which is, oh, you can't even see what I'm pointing at. I really would like to point to something. So, there, no, we got it. Okay, good. So, yes. So for any two functions f and g, if many linear combinations are gamma prime close, then fg together are gamma prime plus epsilon star close. And the gamma prime is anything going up to gamma. So gamma is the radius up to which I'm giving you proximity gaps. So these are the definitions of, this is what proximity gaps means. And what we want is, and we want to get proximity gaps for Reed-Solomon codes. I will just very briefly summarize why we care about this. I guess to this audience, maybe I don't need to say this, but okay, I'm just saying this. General computational claims reduced to proximity claims to Reed-Solomon codes. A claim of the form, this function is close to Reed-Solomon. A single proximity claim to Reed-Solomon codes can reduce to several proximity claims to smaller Reed-Solomon codes. This is an FFT-like decomposition. And finally, several proximity claims can be combined into one by the proximity gap statement. So this is how proximity gaps fits into the whole picture of everything. And the things that do this are, for example, the Fry, Stir, and Whir protocols, which it sounds like everybody here knows. Okay, great. So some more notation. We're talking about Reed-Solomon codes over FQ with evaluation domain D and degree K. So polynomials of degree K evaluated over D. And the K is going to be 1 minus delta times n, where delta is the distance. And I'm going to say everything in terms of these letters. Good. And what we want out of a good proximity gap result is gamma as large as possible, A as small as possible, and epsilon star being little o of 1 would be is nice. 0 is even better. And these are things that can be used in analyses of things like Fry, etc. And and you cannot take gamma as large as delta. This at that point you need a huge. This is a trivial result. So maybe one could hope that for every gamma less than delta, you can have a small. And how small? Maybe a being poly n, maybe a being. I mean, one could have conjectured a lot of things, and in fact it was conjectured, and it was famously disproved 5 minutes ago. Yes. So what you have to be careful about what you want to conjecture, but it's not. Yeah. I mean, sometimes a lot of things like this do work out. In this case, we found out that it doesn't. So the big question is how to make gamma as large as possible while keeping a small and epsilon star almost 0. And sometimes epsilon star being exactly 0 is important. This shows up in the Stir and Whir protocols, but epsilon star being little o1 is also a respectable question, which we should all think about. Okay, and so I'm going to say what the latest known results about proximity gaps in the positive side are prior to our work. There are 3 kinds of results. One of them is up to half the minimum distance. This is gamma going up to less than delta over 2. Then we have proximity gaps with n exceptions, so a being n, and epsilon star being 0. So there's 0 proximity loss, and there are only n exceptions. So the soundness error, which is this a over q parameter, is now n over q in if you use this, and maybe you would set q much bigger than n, and you get a nice proximity gap result, which you can use. There's another version. This goes up to the Johnson radius. The Johnson radius is the best list decoding radius that we know for Reed-Solomon codes in general, and there we get a bound of when gamma is less than slightly less than the Johnson radius, we get order n square, a being order n square. So you would have to set your field size so that n square over q is as small as the soundness error you want, and epsilon star being 0. And there's also this annoying eta to the 7, which depends on the gap. And okay, this is what it is. And there's a third incomparable result, which achieves a different kind of proximity gap, which is which works up to this 1.5 Johnson bound. And it says that going up to 1.5 Johnson bound minus eta, you can have a being really small. This is a constant. This is only gamma over eta epsilon squared. And so this has its own merits despite the existence of those other 2. And this is the status of the best known proximity gaps results for Reed-Solomon codes prior to what I'm about to say. Great. Questions about the setup or my letters? Okay, good. So I'll tell you what our main results are. Our main result is better proximity gaps for both up to delta over 2 and up to the Johnson radius, roughly improving the previous results by a factor n. So when when gamma is less than delta over 2, so up to half the minimum distance, we can get proximity gaps with a being, this is a constant, if epsilon star is a constant. So you set epsilon star to be 0.01, and this a is a constant, bounded by whatever this is. So there's no n involvement in this. But it depends. I mean, I guess in application, sometimes n is epsilon. I mean, n is not so huge that you don't want to pay the n penalty. So, I mean, this is the quantitative behavior of this. So this improves the unique distance decoding result from the paper BCIKS, which was from n down to this constant. And our second result is improves the BCIKS result up to the Johnson radius by changing the n square over eta to the 7 down to n over eta to the 5. And I mean, so I guess the n, right, and this achieves it with 0 proximity loss. So the previous result also achieved it with 0 proximity loss, and this is the statement here. And the constants in this big O are all very reasonable. Okay, and so this is the statements of the main result. Questions about the statement? Okay, great. Well, I'm going faster than I thought. Great. So this is the table of everything that was known before. I also want yeah, this is the unique decoding statement that I just said. This is the list decoding statement that I just said, up to the Johnson radius. There was a paper also just a couple of days ago, or a day ago maybe, by Goyal and Guruswamy, proving this amazing result that for random Reed-Solomon codes, one can have list decoding, and one can have proximity gaps up to radius delta minus eta, with A being linear in n, with proximity loss 0. This is for random Reed-Solomon codes, and it also has this extra condition that Q has to be at least 2 to the 1 over eta square. I guess this was somehow, this is an important thing that makes it consistent with all the impossibility results from last time. I learned. Okay, great. So these are, I mean, some Reed-Solomon codes are do have amazing proximity gaps, but these are random Reed-Solomon codes, and my understanding is that if they're like the list decoding results, we don't have an explicit criterion for when you sample the random evaluation set whether it works for you. But most Reed-Solomon codes where you choose the evaluation domain at random do have really good proximity gaps, just like they have good list decoding from other work from before. Okay, so these are the positive results. So I'm going to now give some flavor of what the idea is that helped improve. So if you know something about the BCIKS, oh, I see a question, but okay, let me just say finish my sentence. So if you know something about the BCIKS result, so there was, this then, so it had some simple parts and it had some complicated parts, and we're going to improve one of the simple parts. So I don't know if that's good or bad. Okay, great. So I'm going to start with the outline of how BCIKS proves this, and I will talk about how we change, what changes there to give us the quantitative improvement. Okay, so what is our set? What's the problem? We know that F plus Z times G is close to the code C for many Z's. Okay, we want to deduce that F and G are jointly close to two true polynomials, capital F and capital G. That's what we want to do. Okay, so how are we going to use the information that F plus Z times G is close to C for many Z? So the idea is to replace the multiple little z's with one capital Z, the formal variable Z. And we look at the field of rational functions in this formal variable Z, and you look at F plus capital Z times G. This is a function from the domain D to the field K. At every point, it gives you, if you look at it, it gives you a linear function in Z. And we're going to view this as the received word for a Reed-Solomon code. Which Reed-Solomon code? It's the Reed-Solomon code K over the field K. This is a huge field. You would never use this Reed-Solomon code, but it is a field we can think about. We can use this, we can think about this Reed-Solomon code. There is a D, and the same domain D, which is a subset of the field FQ, but it's also a subset of K because K is even bigger than FQ, and K the same degree. And this F plus ZG is, we view it as a received word, and the main idea is to decode it to a nearby code word of this Reed-Solomon code. That's what, I have to talk about how we decode it, but that's what the proof will try to do. Once we have decoded it, we will then see that, oh, actually any code word C of X in this Reed-Solomon code that is close to a received word of this form, F plus ZG, is actually of the form capital F of X plus Z times capital G of X. So it's actually a true polynomial in X plus Z plus Z times capital G of X. And these F and G turn out to be the elements of the original Reed-Solomon code C that are close to F and G. This is the high-level outline of how we are identifying the capital F and the capital G, and the true code words F and G, which are close to little f and little g. And yes, the crux is how to decode it. How do you decode it? Well, we will run a known decoding algorithm on this received word. This run is only in the proof. It's not an algorithm that anybody's run. It just, the proof is going to imagine running a decoding algorithm on F plus Z times G. As it's running it, it's going to try to do some things. We won't know whether to make some steps succeed. We will keep going back, substituting capital Z back to little z, using this knowledge that F plus little z times G is close to C. This will help this will help our decoder run. And we will show that this decoder does succeed in its run and end up with a nearby code word. So in some sense, algorithms give you an algorithm for decoding gives you a criterion for whether a string is close to the code or not. I mean, it is also an efficiently implementable criterion, but for the proof, it's not relevant that it's efficiently implementable. It's just the fact that it is a criterion, and it's one we can reason about. So that's what happens here. Okay. And so, when we prove our result for gamma less than delta over 2, it used the Bernekamp-Felts decoder. When we proved for gamma less than Johnson radius, it used the Goswami-Sudan decoder for Reed-Solomon codes. Both of these are really beautiful algorithms. If you haven't seen them, I highly recommend. They both have, I guess, one-page proofs and analyses. And okay, so now I'm going to say what changes and improves. So both these proofs they use interpolation as their first step. The first step is to find a polynomial q of xy that vanishes on the given received word. So you're given some points, your received word is the graph of something that is supposed to be a polynomial. And we interpolate a bivariate polynomial q of xy that vanishes on all the points of that graph. That is what the first step of both these algorithms is. In the Berlekamp-Welch case, the polynomial q of xy is a very special form. It has this error locator polynomial times y plus some other polynomial. That's what, yeah. And in the Guruswamy-Sudan case, it's much more. It's a general bivariate with higher degree. And when you run this interpolation, in BCI case, the interpolated polynomial ended up having z degree being n. And why was it? Because, well, the algorithms are there. We just followed the instructions in those algorithms, and it gave us n. And I guess in BCI case, what the proof was following the instructions of the algorithm and not questioning it, because it's a famous algorithm. Good. So so what changes now is that we will make this z degree O of 1. And we will make it O of 1 by doing some mild modification to the interpolation problem. That mild modification will introduce extra slack. It will increase the x and y degrees to some extent, and this will you will pay for it, but you pay for it in a place where you don't care. So this is the best kind of payment. Okay, so now I don't want to dive into the details of this. What I will now do is give you a completely isolated, self-contained example showing this phenomenon where something of degree omega n becomes something of degree constant. And I hope everybody can understand. You don't need to know anything about anything for this. Okay, good. So here is the problem. I have an n cross n plus 1 matrix whose all of whose entries are degree 1 polynomials in the variable z. Okay. And I want to find a linear combination of the columns that equals 0. Okay, so that is, in other words, a vector v. And I want to find a vector which I write over here and multiply by a, and I get 0. And I want that vector v to have as low degree as possible. This is what the question is. And this is exactly the kind of question that we face in the interpolation step of these algorithms. And the question is, well, how low a degree can you get? And the answer is, there's basically only one answer. In general, when you have an n cross n plus 1 matrix, there's if it's not singular, oh sorry, it is singular, we know this. If it was random or something like that, there's only one formula for the unique vector in that kernel up to scaling, and that formula is given by Cramer's rule, and it's the v that you get out of it is degree n. It is some determinant of it is a various n by n determinants of this matrix. That's what the v is, and there's no other choice. Good. So in this problem, when you have an n cross n plus 1 matrix, when you're looking for a v in the kernel, the v has to have degree at most n. This is one fun fact. Now I'm going to give you a slightly different question. This is the second example. I have a matrix A, which is not n cross n plus 1, but it's n cross n plus lambda n. So it's 1.1 n up here instead of n plus 1. And now I ask you, I want a v in the kernel. Now v is slightly longer, right? It has length n plus lambda n. I want a v in the kernel with low degree. How low a degree can you get? And one solution to this is zoom in on n plus 1 of these columns. We know that they're linearly dependent, and use Cramer's rule, and it will give you v with n plus 1 non-zero entries, all of them being degree at most n, and the rest of them 0. But that is an inefficient use of everything given to us. We have the ability to use more of the coordinates of v, and maybe we should. And the answer is we can have degree constant, only depending on lambda. And in fact, it's 1 over lambda. The degree of v can be 1 over lambda. It does not have anything to do with that. And this improvement in the z degree improves things inside the proof. And I can now prove this if we have, I will take one slide. I think I have time. Do I have time?
Go ahead.
Oh, great. Okay, so good. So I'm looking for a vector v of degree d, which sets that av is 0. Okay, so I'm going to take each entry of v. There are n plus lambda n such entries. And for each one, there are d plus 1 coefficients, because the polynomial degree d has d plus 1 coefficients. And I'm going to call all of these unknown variables. So they're totally d plus 1 times n plus lambda in unknown coefficients. And yeah, this is how the system looks. And when I multiply this with this, what I get here is a polynomial. Each entry of this polynomial, if this has degree d and all the entries of A have degree 1, the product will have degree d plus 1. So we have these polynomials sitting here, which are the coefficients of that are formal linear combinations of the unknown coefficients here. And each one is degree d plus 1. So each one has d plus 2 coefficients. And there are n of them. So totally, we're asking that n times d plus 2 different linear combinations of these variables end up being 0. So there are n times d plus 2 linear equations that we need to satisfy. There are d plus 1 times n plus lambda in unknown coefficients. If the number of unknown coefficients is more than the number of linear equations, then there's a non-zero solution that makes this happen. The math of that is d plus 1 times 1 plus lambda n is greater than n times d plus 2. The n cancels and d can be 1 over lambda. And so there is a non-zero solution. So in this tiny toy example, but it's not very far from what happens inside the proof. We see that you can get drastically lower z degrees for your solutions, provided provided you had a little bit of extra slack. The system of linear equations that you're solving, if it is slightly if it's barely underdetermined, then you can't do anything. But if it's slightly underdetermined, then you can do much more. And what this translates to in terms of the rest of the proof of Berlekamp-Welch and Guru-Swami-Sudhan is that you now have interpolated a polynomial of slightly higher x and y degrees. So, for example, the error locator polynomial that you would get in the Berlekamp-Welch decoder, it's not of degree the number of errors. It is more than that. It is maybe 1.1 times the number of errors or something like that. And this is also okay, provided the number of errors is bounded away from half the minimum distance. And one has to work through that and see that it all works. Okay, great. So I will also quickly state our main negative result. We have a bunch of negative results. Some are more main than others. So here is one which is maybe most relevant to the first part of the talk. It is an example where proximity gaps need A to be large. If you want proximity gaps, you want A large. So this is in a slightly different setting from the previous talk, so in the previous talk, we were talking about distances very, very close to the we were talking about the radii gamma being very, very close to the distance delta. Now we're going to talk about gammas which are substantially closer, as close as the Johnson radius. So if you take FQ with Q even, and you take D, the evaluation domain, to be a random F2 subspace of size about square root Q, and you look at polynomials of degree constant fraction times n, okay, and consider this code, then the statement is that if you want proximity gaps for C with loss smaller than 1/8, this is quite loose bound, or rather, I mean, we're accepting quite a lot of loss, and the radius of your proximity gaps is as big as the Johnson radius, then you must have A almost all of Q. And in that case, Q is about n squared. And yeah, so this means, more concretely, there are two functions f and g such that f and g jointly are 1/8 far. Oh, sorry, not 1/8 far. They're gamma plus 1/8 far from the code, but almost every linear combination f plus zg is gamma close to the code. Almost everyone. So it's really disturbing. Okay. And so this is a summary of all the negative results that we have. So we have a whole bunch of assorted examples. The two, I guess, most interesting ones I would say are these two highlighted ones. This was the one I just mentioned about where if you go up to the Johnson radius, you need n squared. So we saw that if you're within the Johnson radius, your Johnson radius minus eta, then the A can be n. But the moment you reach the Johnson radius, it jumped to n squared. That's what this says. And the next example shows that, yeah, you can start getting into the tau type behavior also for any constant tau. Also within not all the way at the distance delta, but at some constant distance away from delta. And so bad things are happening for proximity gaps, at least for Q being even. And we have some other examples which work for Q being primes. None of these are, these do not have constant proximity loss. They have little or one proximity loss. And the previous talk of Diamond and Gruen is here, and there's also the simultaneous work of Kreitz and Stewart, who prove this. And and there's some tight connection to the list decoding radius, which is also done by Kreitz and Stewart. And great, so this is this. I'm happy to take questions. So I see one, how sensitive are they to the size of the domain? Also the choice of domain, they're very sensitive. Here, so it turns out, so the counterexamples, the ones up here, they work for most subspaces, but the fact that it is a subspace is extremely important for this counterexample to work. And as we know that random evaluation domains have good proximity gaps. So yeah, so there's definitely, the structure definitely matters. Great, so let me look at other questions. I'm jumping to the latest and I'm going in backwards order, let's say. For binary shape, the evaluation, it doesn't hold for every subspace. It only holds for a random subspace. If that subspace happened to be a subfield, it would not hold. The proof requires it to be the proof, so almost all subspaces work, but we know examples of subspaces where our method does not work, namely subfields definitely do not work. And yeah, okay, so any other questions?
Thank you, Swastik. I don't see any more questions, but I'll give it a bit of time for people to chime in. Thank you so much for your presentation. I guess I have a question. So the n squared for the Johnson bound was improved to n, and eta to the 7 was improved to eta to the 5. Like, do you feel like we can go further either in the numerator or the denominator?
Yeah, so the n going down cannot happen because of the first example up here. It cannot happen for all choices of delta because of the first example up here. But so I think the most interesting question is maybe over prime fields, there's some amazing proximity gaps that happen just because you're working over a prime. So it's potentially true that prime fields have great proximity gaps. We have no substantial counterexamples. Let's say, right. I mean, so for example, Ben and Angus's conjecture, apart from, yeah, I mean, that may be completely true over prime fields with absolutely no loss. And I think that's potentially good. That eta to the 5, I know Antonio Sanso has an improvement which possibly composes with this. So it might become eta to the 4. And yeah, that shouldn't be fundamental. It should go down. I expect the exponent of eta, but n has to stay there.
Interestingly, we haven't seen these binary fields be used that much in production. You know, one of the reasons being that they may be less friendly to GPU acceleration. Like, are you saying here that there's a separation between binary fields and prime fields, and maybe binary fields are less attractive from a proximity gaps perspective?
Yes, I think so. So we similarly know better list decoding counterexamples over small characteristic fields compared to prime fields. So prime fields, we don't know that list decoding up to capacity. It could be that the list size is constant, independent of n, while for fields of small characteristic, we know that the list size has to grow. It has to be polynomially big, and it like n square or n cube as you approach capacity. So in general, yeah, the list decoding and the proximity gaps behavior of small characteristic fields is worse than for prime fields. And for prime fields, potentially everything we ever hope for modulo the recent counterexamples is true.
Alim is asking if there's like numerical data or experimental behavior that kind of helps us analyze these proximity gaps, I guess on maybe small fields or small examples.
yeah, so these things are very, very tough to test because the search space is not just code words, but it's the search space is too much. I don't have any way of doing it. But I mean, there are, I mean, if you already make up a plan of how you want to make a proximity gaps counterexample, maybe you can get a more directed search. So we have some examples of this. So this line over here about merge cell prime Q, you can do it over basically any prime Q by searching for the appropriate subgroup with the right additive combinatorial property. But this was after you have to put in one idea before, to narrow your search space. Otherwise, there's not much computer search that can help it.
So maybe can I just ask a question directly? Swastik, you mentioned, so I think you said that maybe there's this ideal world where we have perfect proximity gaps for prime fields or something like that, right? I guess, I mean, I'm biased. We have our revised conjecture. I'm actually wondering why not just let that be the ideal world, right? Because there's nothing about characteristic or domain. All you have to do is not let your rates go to 0 and your shortfalls go to 0. But isn't that enough for most applications? Like, wouldn't that be a suitable substitute for the proximity gap theorems that we have?
Oh, that's a good one. So yes, so by everything we ever wanted is that conjecture also with the exponent being 1. Let's
okay.
So it's an even stronger version of your conjecture where you insist on the exponent being 1, and then I think maybe you're okay.
Interesting.
So n to the 1, or maybe even n to the 0. I don't know that it can't be n to the 0. Maybe it's a constant. Why not? So, but over prime fields that could still survive, that cannot hold over small characteristics because of these kinds of examples. And at least we know that the exponent has to grow as the distance approaches 1.
Yeah. From a practical perspective, I think that the fact that n is now 1 for the Johnson bound, actually when we were looking at going to proven security, we actually were looking at the unique decoding radius in part because n's 1 there, and the sort of field size required for the Johnson bound was much larger. So similarly, it would be great if n could stay 1 past the Johnson bound, but just the fact that it's gone to n equals 1 for the Johnson bound with this work is like I think a big practical improvement on the proven security side.
Okay, that's good to hear. Yeah.
For sure.
And it could potentially go smaller than n to the 1 for prime fields. We do not know that you need n equals. You even need the n to the 1 for prime fields. This
with a small proximity loss, right? Which I think is another great and interesting part of your newer work is to allow proximity loss. And this seems to really strengthen what you can get just for paying a small penalty there, and you can get much better exponents and things like that, right?
And there's also this other Diamond and Gruen conjecture, which is that every linear code might be might have proximity gaps up to half the minimum distance, which is that's an amazing possibility.
Sure.
We're out of time. Thank you so much, Swastik, for this great presentation and groundbreaking results. Congrats to those who made it to the end, 124 participants. We're going to have one last presentation and we're going to overflow a little bit. So it's a 20-minute discussion with Giacomo on the proximity prize.
Okay, can you guys hear me?
Yes, and we can see your screen.
Okay, perfect. These are two good starting points, I think, for any presentation. All right, guys. Okay, so look, we've heard a lot about the new written results about proximity prices, and so I want to give like a bit of an update of what me and Dan and some other people have been working on, plus give like a little bit of like some context about these results, end up actually touching the concrete side of it, so the actual proof system which are deployed. So, okay, let me just give a reminder at an high level what this proximity price is. So this is like this initiative by the Ethereum Foundation in which we want to incentivize people to work on this beautiful question that luckily people are already working on the Reed-Solomon conjecture about proximity gaps and list coding. And one natural question you might ask is what is actually going on with the price? What is the status of it? What have we been doing? There's been a lot of progress, not from our side at the moment. affectionately, I wanted to call this the mesis mirabilis. In reality, it's an hebdomas mirabilis, because it's been like just a week in which a bunch of wonderful papers have been come out about these exact problems. So this started from like the Ben and Angus result, which was then followed by Elizabeth and Alistair's, giving like some negative results on like where these proximity gaps can hold in general. Then there was this wonderful paper by Goyal and Goswami about showing that, in fact, for like a wide families of codes, you can actually achieve almost optimal mutual correlated agreement up to capacity. Then there was a Swastik paper that was just presented about both negative and positive result regarding Ritz-Solomon code proximity gaps. There was another paper today about list decoding of Ritz-Solomon code with determinism, which is also very exciting to see. And finally, there was the paper not on ePrint yet about from Ziyi and the others about strengthening mutual correlated agreement for all kind of polynomial generators. So there has been a lot of things that happened. There's been a lot of results. And the next slide, I'm going to kind of figure out, I'm going to present a bit how these fit in the landscape, how they go and affect the efficiency of the proof systems, and some of the things that we've been doing in the committee regarding this, regarding the proximity price. So the big overall TLDR, you know, is that we're working on writing up the results. We're trying to formulate some watertight version of the conjectures, which are consistent with what we know reality is after these new results, and also present a survey on how this, on what is the status of what things are known at the moment. So this is the big part of it. Of course, when you get this many results coming in, you know, we've had to amend our paper a few times. So me and Dan have been working hard, and you'll get more news on that front from us soon. So let me give you some background. I just want to do a zip. We've seen a lot of other things. So I'm going to actually, so we've been talking about error correcting codes, and a lot of the questions we're going to be asked for the proximity price actually relate more generally to linear codes. And the parameters of interest that we really care about for these linear codes are really three things. One of them is the minimum distance, and the reason why minimum distance of a code is important is because it translates to verifier efficiency. So the larger a code, the minimum distance of a code is, the more efficient we can have the verifier, which impact in particular proof size. We want also the two other metrics of interest to be small. This is the rate of the code, which is a measure of the amount of redundancy that the code has, and then translate in how much hashing the prover needs to do. So the smaller the rate, the more hashing the prover will need to do. The other metric of interest is the encoding time, which directly transmits to prover time, because the prover needs to actually perform at least one encoding. And I'm going to be talking a lot more about list decoding soon. This is also another interesting feature about the code. And the code that we care about in the survey for practical deployment is that of Ritz-Solomon codes, which will be evaluation of polynomials of some degree less than k on a domain of a certain size. So why, for some motivation of why these codes have been very influential for like practical snarks, is that they achieve like this optimal rate distance trade-off over large fields, over large alphabet, which is the singleton bound. So in particular, the trade-off between how much work the prover has to do and the efficiency that the verifier can hope to achieve is optimal over a large alphabet. Further, the encoding time is an FFT. And so while the proving time is not linear, FFTs have been widely studied. There's a lot of amazing algorithms, and they're also very parallelizable. So this is the code that like a very sweet spot in terms of being extremely efficient and also achieving very good trade-offs. And so this has been used in a variety of works since like their introduction in the 1960s. Here I've tried to survey all the Ritz-Solomon based protocols that are known in the literature. So as you can see, there's a bunch of them. And so studying this is the reason why we focus on the Ritz-Solomon case for this proximity price. Yeah, while, even though these questions are interesting in general for a much wider class of codes. So what maybe following the tradition of what's been going on with the Fry and ETH star things, I want to present like a small toy problem that we've been playing around while formulating the conjecture. That is a minimal example of a protocol whose security encompasses basically all that we need for the security of like larger protocol. So this is going to be a simple protocol. So the claim is that you have two messages, F1 and F2. You have encoding of them, and some linear constraint should hold over the messages. So in particular, these are in a sense they're linearly constrained codes. So I have an encoding which needs to satisfy some constraint. I have two pairs of them, and I want to find a very tiny toy problem to actually test these constraints claims. So this is kind of the setting. I have my F1, F2. This will be encoding, so these green parts represent the redundancy that I'm going to add. And I have a prover verifier. And the protocol that we want to analyze is a very simple one, in which what will happen is that the verifier will ask the prover to provide a random combination of the two messages. So this gamma is the random combination randomness. According to this randomness, the prover will send an F1 and an F2. The sum of F1 and F2 scaled by this randomness. And then the verifier will sample some indices, and it will check two things. First, it will check that the combined function satisfies the claim. And further, that when you encode the message being sent by the prover, and you can query F1 and F2, you actually have agreement. And what I claim is that this protocol ends up being simple enough, but in particular, completeness, for example, is obvious. But it's actually the soundness analysis of it is sufficient to encompass basically the soundness of much more complicated protocols. In particular, things like WER can be directly analyzed by thinking about this building block. So this is the toy protocol. It's relatively simple, and you can give a very nice security analysis in which you show that the security of this protocol is the union bound of these three terms. One term will be distance preservation, one term will be related to the list size, and one term will be related this 1 minus delta of the t. This is like the spot check error in a certain sense. In fact, you can even show that this protocol satisfies much stronger properties. So you can show that this actually has a round-around knowledge soundness, even without assuming that the code is a error-tolerant error decoder. And this analysis works for every delta. So if I give you a bound on list size and a bound on the mutual correlated agreement error, I can show a bound on the distance. So a bound on the soundness error. So I'll tell you a bit about what these errors are in practice. So in particular, what their behavior as the distance goes to 1. And another thing, the efficiency of this protocol is basically determined by what this parameter t is. So what's are interesting is that to make the term 1 minus delta to the t as small as possible, we want to increase delta to go towards 1. And the trick about choosing soundness for this protocol is to balance between these errors. In particular, the MCA error will go to 1 as the delta goes to 1. The list size error is even worse because this term will actually blow up exponentially as the delta goes up to 1, while this latter term will go to 0 as delta goes to 1. So obtaining efficiency in this protocol is basically finding the delicate balance between minimizing t and maintaining all the other errors small enough. And this toy problem is what we're going to be using to kind of inform our decision on what problem to think about for the proximity price and what kind of regimes we can tolerate. Good. So this is our simple toy problem. And I'm going to tell you a bit about the regimes of interest. We've heard a lot about it today, but I'm going to do a little bit. So I'm going to, in this case, I'm going to fix a rate is equal to 1/2, because this is the setting which is more of practical interest. I'm going to take this line. This is the settings of delta that we can choose in the previous protocol. And now I'm going to partition it in regimes according to where we tend to have sharp phase transitions in these errors beforehand. So the first area that I want to talk about is this part here. This is the unique decoding radius, which spans from delta is equal to 0 to 0.25. The next regime is that of the Johnson bound. The Johnson bound for rate is equal to 1/2 is between 0.25 and 0.29, this regime of interest. And then there's this new area, which is after Johnson bound, which I've put here like Ixon Dracones. This is like the area where we don't have provable guarantees, but we nonetheless would like to be there for like for efficiency. And there's also another area here, which is the 1.5 Johnson bound, but for simplicity, since we're in the case where rate is equal to 1/2, this is covered by unique decoding, so we don't have to think about it for now. Okay, so what we know is that in fact there's an area, a red area, which is where the, sorry, I cannot even see it because I have, give me just a second. Okay, there's an area which is this 0. Up between 0.5 and 0.49, which is where the combinatorial attacks of Ben, Angus, Elizabeth, and Alistair ended up to apply. So the area which the conjecture is really concerned is this area in the middle, which I'm going to call informally the capacity regime for now. So this is between the Johnson bound and where we know that these attacks end up applying. To tell you a bit about what concretely this ends up, how concretely this ends up mattering for like systems, the runaround error 1 minus delta to the t is what informs the number of queries that the protocol needs to do. So for the toy protocol, you can see that this is the number of errors that the number of queries that you need to do. And particularly CB, this is the optimistic bound. In fact, it will be larger due to Angus, Ben, Elizabeth, and Alistair's attack. And with modern proof systems, such as Stir and Whir, the argument size is dominated by these T-Merkle paths. And basically, you can use this to estimate what the proof size of the protocol ends up being. So as you can see, the argument size decreases when we move towards more aggressive regimes. Good. So these are the regimes that we are we're interested in. Good question so far? I don't know if I cannot see the chat if there's anything, but let me know if there are questions.
There is one question. If we rank the difficulty of the computer science open questions from 1 to 10, with P versus NP being 10, how hard is the proximity prize question?
I would say that since the new relations between list decoding and corrected agreement, this seems to be at least as hard as list decoding for each Solomon codes. And this is a very hard question, so I'm gonna give it like maybe an 8 or a 7.
Okay, wow. Is it because list decodability has been open for many decades?
Indeed, yeah.
Okay, got it.
But maybe, yeah, 7 is good because there's been progress towards it, while for other problems, we don't even know where to start. Okay, good. So let me tell you a bit about list size, which is, so what we're planning on doing, and at the end, I think this will be a good place to discuss is to conjecture 2 problems in this proximity prize. One of them will be related to list size of each Solomon codes, and the other one will be related to corrected agreement. So what's list size? Well, the question that I am asking is that I have some word, and I know that within like distance delta over C over 2, there will be at most one single ball nearby, but once my delta increases past this point, there might be many more balls and many more code words nearby. The list size question is about giving a bound for how large the list ends up being. And the intuition why we need this is because list size figures out in a toy problem, and it ends up spoiling the soundness error. Particularly, there are two places. One of the places where it appears is in the outer domain samples, and the other part is this constraint fold, which also appears in the toy problem. Another motivation for why this list size is an interesting problem to study is that we can most likely, even if CA does not hold up to capacity, we should be able to obtain a slightly less efficient version of our protocols, which only rely on list decoding up to conjecture. So this, in a sense, is the most fundamental of the two assumptions that we are, this conjecture that we will be conjecturing. And in fact, thanks to the recent result by Alistair and Elizabeth, and also from the new paper that came out this morning, it does seem that like progress in correlated agreement will also imply progress in list size. So this is so there's a very tight relation between these two problems, as I think will also be evident when we look back at the regimes later on. Again, I'm going to be focusing with Solomon code, but this is an exceptionally interesting question to ask also for general linear codes, or for array codes and expander codes in general. So what is known is that something quite similar to what we actually know in for correlated agreement. So in unique decoding, by definition, the list size is a single closed code word. Up to Johnson bound, we know that the number of code words will also be small, will be roughly linear in the evaluation domain size. We know in a similar area to where Alistair's Elizabeth, Angus, and Ben attacks hold, that this list size will grow to a super polynomial size. And there's some questions about what happens in this area, in the Ixon Dragones one that I was talking about before. And our hope is that in this area, the number of code words that you end up having is something that we can handle. So we need the list size to be small with respect to the size of the field. So if this is a small polynomial in the evaluation domain size, is something that in the soundness error we will be able to handle. And there are some limitations for what we can achieve here. So for example, if for rich Solomon codes over full domain, the list size ends up being super polynomial not much after Johnson bound. And when we're getting close to capacity, there are also some other limits, similarly to what Angus, with the recent attacks on rich Solomon code on MDS codes end up showing. On the upfront, we know that in fact for some families of code, in particularly randomly punctured Solomon code, over a sufficiently large alphabet, with that probability, we expect this list to be small, and in fact this list to be optimally small, which is really exciting. What's the situation with distance preservation? Well, I'm going to skip this slide because we talked about a lot about different notions of correlated agreement. But what is known is very similar to the case of the list decoding. So if we look at the previous settings, we know that below minimum distance over 3, we have these errors. This was known from like early work such as Ligero. Then from the previous work in proximity gaps, we know that for each Solomon code up to the UDR, we get linear error. And in fact, thanks to the new result, this can be further improved. We further know that up to Johnson bound, we managed to get a mutual correlated agreement with a quadratic error. And we also know from the attacks from the attack that I was mentioning before that after when you're close enough to capacity, the error of mutual correlated agreement becomes essentially 1. Further, from just a few minutes ago, we know now that the error from the UDR to the JB area can actually be improved to a linear dependency. And the question that we ask, similarly to the list decoding case, is what happens in this area between where the attacks apply and when the Johnson, where we know the results improvable from the Johnson bound. And again, there are some limitations that we need to do, most notably the new attacks that were presented. There were some limitation on full domain with Solomon codes, and there are some new limitations from the paper also done. But also thanks to like some other development, we actually know that a similar situation to what we have in list holds up in the for correlated agreement, in that random codes end up having a mutual correlated agreement with almost optimal error, so linear error in the field size, up to very close to capacity, as long as the alphabet is large enough. So this is extremely exciting to see. Good. So this is kind of like the status of what we know after the past week, which has been a very hectic time of updating these slides. And yes, and the way I want to interpret this return result, this GG25 result, is that morally we are matching whatever we knew about list decoding up to capacity, translating it to mutual correlated agreement, which is a very exciting development. So just to conclude, I think I'm almost right on time. So it's been really exciting and a privilege to see all the progress so far that we've seen on the theory side. And honestly, when this, I wasn't expecting this much progress in so little time. This has been extremely hectic, but extremely exciting. So we're gonna be trying to stabilize the conjecture, release a survey soon of what's been going on, and hopefully we don't get a paper every day for the past month because that's too much work. And I want to highlight some other proximity prize related effort that has been going on in the past months, and particularly spurred from like the Cambridge workshop that has been organized by Justin and Will. So one thing is this numerical effort that's been spearheaded by Antonio on trying to, for very small field sizes, evaluation domains, trying to numerically check whether correlated agreement holds or find counterexamples. So this has been exciting work where I think it should be, we are looking for more help. I think there's a lot of ideas that are floating about and not enough time to implement all of them. So having help on this would be extremely exciting. Further, one thing that we won't plan to really include with the Proximity Prize is to synergize with the formal verification efforts that have been going on at the EF. So in that, there's also a lot of work about formalizing the statement of the conjectures and hopefully formalizing proofs and disproof of therein. So this has been kind of like a bit Russian update on all that's going on. And I want to thank Justin, Benedict Wagner, and the OLEF for all the support for this Proximity Prize. It's really been a privilege to be able to see all the progress that's been spurred by this. And I think now, I don't know how much people have to go, but I'm happy to take questions, discussions about the format of the prize, the conjectures, and everything.
Thank you so much, Giacomo. Any questions from the audience? And I must also say it's been an absolute pleasure working with you, and I'm so pleased that you're part of the jury. I guess I have a question for Dan, who might still be on the call. I'm not sure if he made it.
Yeah, I'm here.
Okay, great. I guess, Dan, do you have a few thoughts on the Proximity Prize, and what's your take, I guess?
Yeah, of course. I think the main thing is just hang tight in that we haven't formalized the actual conjectures yet. And of course, all the recent work has been causing some delays, but this is fine. It's all super interesting. Yeah, so I guess one of the issues that came out of the discussion today is also the fact that the exact field that we're using should also be incorporated into these challenge questions in the prize. So you'll see some of that in there as well.
Right, and the exact evaluation domain as well, potentially.
Exactly, yeah.
Nice.
Okay, can I ask you a question? So how will you make sure that if you specify particular parameters, particular field, you're not kind of missing the most interesting results by overspecification of the challenge problem? Challenge problems.
Sorry, could you repeat that?
Yeah, there's a risk of kind of overspecifying the challenge problems and sort of the result of that field, but then implementers move to another set of fields that avoid attacks. How will you avoid that problem?
So
Yeah, I think the challenge problems are going to be quite general. So it will encompass basically all the entire design space. And the goal, so there'll be challenge problems that are very generic, and then even we've been debating whether things should be asymptotic or concrete. So we'll have different flavors of the challenge problems. But I wouldn't worry about this, Daria. It's going to be quite generic, and it will encompass the entire design space.
Thank you.
And I would also maybe mention that currently I know that a lot of techniques that we've been using for like counterexamples and proofs, apart from the binary field case, do seem to be very field agnostic. Seem to be very kind of hard to use a structure of the field efficiently when we're talking about large prime fields. So the hope is that if this trend continues, is that any result that we get will be general enough to encompass a wide variety of fields as well.
Though I have to say, it would be really quite bizarre and really interesting if it turns out that there's like a very specific family of fields, say a specific family of primes for which proximity gaps are especially good. Yeah, that would be quite interesting. The techniques we have today don't seem to go in that direction, but that might be because our techniques are relatively weak. So just throwing it out there that it might be interesting to look even for specific primes and specific domains where things are better.
One question in the chat: how do you imagine the 1 million prize to be split among various partial results and the full result if and when it is proven?
That sounds like a question for you, Justin.
I mean, the way that I think about it is that we have this area of uncertainty stuck between the positive and the negative results, and we need to kind of find a way to quantify improvements. And roughly speaking, the new negative results improve things by, let's say, 3% on the negative side of things. So, like, morally speaking, that should be getting roughly 3% of the 1 million prize, and hopefully we can squeeze this gap all the way to 0 and then allocate the full 1 million prize and have basically a full understanding of these mathematical foundations. But yeah, ultimately, I think we'll be dedicating the rules to the panel of judges, which right now is Giacomo and Dan.
Yeah, it's a good answer.
Will there be kind of a process to handle disputes? Because it's possible, right, that one set of researchers will claim they've solved the problem, another set of researchers will dispute that. What happens then?
Do you want me to answer that?
It's just, yeah.
Honestly, this is still worked out. I think there have been other prizes in the past, like I guess the Millennium Prize is a good example. We'll probably follow, when it comes to the actual rule, we might just follow what other prizes have done.
Okay, yeah.
Okay, we've gone 2 hours and 20 minutes. Thank you so much to the 90 people who've made it so far, and see you soon for Ethproofs call number 7.
Real quick.
Go ahead.
I had just a quick note for those of you that are coming to Ethproofs Day. I dropped a note in the chat, but there's only 250 seats. There's about 500 people on the waiting list. So try to get there between 9:30 and 10 for guaranteed admission if you've been approved. If you're on the wait list and you have attended an Ethproofs call, we try to match those names up after each call. We've got a priority wait list, and so we'll kind of like start letting those people in from 10 to 10:30. So yeah, just come early. We're gonna have coffee early. You can network, take advantage of the time, and we just hope to have like a lot of contributors and a lot of like passionate spectators in the audience, and just try to keep it very high quality group and signal. We're really looking forward to it.
Perfect. Thank you. It's going to be one of the best events of DevConnect. Bye, everyone. Have a great day.
Bye, guys.
Bye.